Welcome to this Engineering Research eSymposium presentation. This is part of a series of online presentations that highlight some of the excellent work being done by our research partners using our technologies. Before we go to today's presentation, I'd like to provide a quick introduction to Maplesoft, why we think it's important to support projects such as this, and how. Maplesoft has over 30 years of experience in supporting advanced research projects. In fact, the company's core symbolic technology, the ability to allow computers to handle problems at the equation level instead of attempting to solve them purely numerically, was developed as part of a research project in 1980 at the University of Waterloo in Ontario, Canada. Since then, many of our highly advanced computational techniques for solving complex analytical problems have had their beginnings in many research projects. Maplesoft is now a leading provider of high-performance tools and technologies for solving a myriad of technical problems in engineering, science, and applied mathematics throughout the world. Our software and services touches hundreds of thousands of people worldwide, and we are well known for our expertise in mathematical and system-level modeling and analysis. We acknowledge that we can only advance through the support of our engineering research projects that require our technologies, and have been recognized as a powerful partner in these endeavors. Specifically, we can provide guidance and support in the development of research proposals through in-kind and technology contributions, as well as helping to foster relationships with other industrial partners. Furthermore, we can provide help in skills development of your team members through training and application development support, as well as providing openings for co-op placement and internships. We also recognize that working with our research partners provides a rich seam of talent that is much needed by ourselves and our industrial partners. Consequently, we've hired many engineers to work within our development and support groups and opened up opportunities for new hires within our customers and partners. Now let's go to today's presentation, the Predictive Simulation of Cycling with MapleSim, presented by Dr. Naser Mehrabi from the University of Waterloo. Naser Mehrabi received his BSc and MSc degrees in mechanical engineering from the Iran University of Science and Technology and Cont'd University of Technology in Iran, and his PhD in Systems Design Engineering from the University of Waterloo. He's currently a postdoctoral fellow with the Motion Research Group at the University of Waterloo, with research interests in sports engineering, wearable technologies, and human-based designs. His research utilizes neuromusculoskeletal and biomechanical modeling via forward dynamic simulation, in addition to experimental biomechanics such as optical motion capture, surface electromyography, inertial measurement units, and mechanical load analyses. He's published his research in several academic journals, including the Journal of Vehicle Systems Dynamics, Frontiers in Neuroscience, and the Journal of Computational and Nonlinear Dynamics.
Thank you, Paul. Today I'm going to present my research on the predictive simulation of cycling. I'm going to start with the research motivation and then go through the I'll talk about the neuromusculoskeletal model we developed for the cycling and its model verification. And then I'll talk about the forward dynamic simulation of this model using a synergy-based optimal control theory. And then I'll present two examples, one in a non-fatiguing condition and the other one for a prolonged simulations, which also considers the neuromuscular fatigue. And I'll finish up with the conclusion and future work. So, research motivation. We are going to develop a biomechanical model to gain insight about optimal dynamics of the cycling. And then we're going to use that to come up with the optimal techniques for our pedaling for a sprint or for the endurance cycling, or come up with a best seat position to produce the maximum power, biomechanical power. Or we can use that to optimize our race pacing strategy. And at the same time, we can use a model to study the injury mechanism that happens in the cycling and how to prevent those, and use those information in the rehabilitation and therapy. So the model we developed in MapleSim is a two-legged cycling model, which consists of 8 segments. The upper extremity part of the model which is here in the figure shown as a hat, includes the head, arm, and trunk, which all we assume they are fixed together and is not moving. And it's fixed at the seat. And the hat part is then connected to the thighs using a revolute joint representing the hip, and thigh connected to the shanks using another revolute joint representing the knee. And here, for just to make our model simpler, we assume that the ankle joint is fixed, therefore the shank and feet is connected to each other. And we are assuming that our cyclist wearing the toe clip shoes, therefore the shoe is always in contact with the crank. And to model that, we use a revolute joint at the toe position of the foot, and the crank also itself is rotated about its central axis. So this figure shows the model which we developed in MapleSim. The red lines at the skeletal muscle, the red lines at the model shows the skeletal muscles. And we have 6 muscles per leg to actuate this musculoskeletal cycling model. And we use the heel muscle model, the figure shows on the right, to simulate the muscle contraction dynamics. The heel muscle consists of the 3 different elements, as shown in the figure. The CE element is the force-producing part of the muscles. And it says that the muscle force is a function of muscle length and also the muscle activation level or muscle activation commands. That's commands coming from our central nervous system or our body. PE is a parallel elastic element, which represents the stiffness of the fiber and tissue, and SE is the series element, which is in series with the CE and PE and represent the tendon dynamics. To model the geometry of the muscles, we use the obstacle set method based on the work of Garner and Pandy. As you can see, the red lines are not going through the knee joints here. They are wrapping around the knee. So we used a wrapping geometry to have a more accurate muscle lengths and muscle moment arm. So then we will have more accurate muscle contraction dynamics in our model. So just to make sure that our kinematic is same, we used a marker, a feature tracking software to track the hip, knee, and ankle and crank position of a real cyclist performing a sub-maximal cycling. And then we compared that to our model prediction, the video on the middle. So there, if you see, the black line represents the experimental data, and the red line is representing the model. And the figures on the right representing the hip angle variation and knee angle variation. The comparison between the model prediction and experiment, you see there are some differences between these two, and these are all coming from our simplification that we did in the model. For example, in the real experiments, the hip joints drops a bit, but in our model we assume the hip is fixed, and also in the model we assume the ankle is fixed, which is not in the real case. But now that we have a kind of good agreement between the experiment and model, we're going to use this model in a forward dynamics simulation to come out with some insight about the cycling. But before talking about the forward dynamics simulation, I'd like to introduce the concept of the muscle synergy first. So the muscle synergy theory suggests that our central nervous system or our body coordinate the muscles in groups and not individually. For example, the figure on the right shows, assume that we have 5 muscles which are color-coded. And so based on the muscle synergy theory, we will have, for example, 3 synergies that groups these muscles with fixed ratio. And our central nervous system just scale those muscles and combine those to get any types of the muscle activation we want. So that helps the reduction of the control space. So instead of controlling 5 variables, now we are controlling 3 variables, which is much easier for our body and also for our forward dynamic simulation. in this case, we are assuming that these muscle synergies are posture dependent. And since in our bicycle model, we just have 1 degree of freedom, that the muscle synergies are just a function of 1 degree of freedom, which here we're just assuming that degree of freedom is the crank. So they are just function of the crank angle. So we're going to use a purely optimization approach to find those muscle synergies. We are going to find the ratio between the muscles such a way that our neuromusculoskeletal model produced a specific torque at the crank. Since the musculoskeletal system is an indeterminate system, meaning that the number of muscles are more than the number of degrees of freedom. For example, here we have 6 muscles per leg, 12 muscles, and we just have 1 degree of freedom. So we need an optimization problem to be able to find a unique solution. So here we're assuming that we're doing a minimization to minimize the physiological cost function. That's something that our body probably do. Here we chose muscle effort. Here A representing the muscle activation and a square just representing its effort. We're doing a minimization to minimize that in such a way that our neuromusculoskeletal model produce a positive torque at the crank. So if we do that for all of the crank angles, we can come up with a map shown here, for example, which we call it synergy. If it produces a positive torque at the crank, we call it positive synergy. What this map represents here, for example, at this point, which is 90 degrees at the crank angle, the most forward position of the crank in its revolution, it just says that to be able to produce a positive torque at the crank, the hamstring muscle should be activated, the G-max muscle should be activated, the rectus femoris muscle should be activated, and vas muscle should be activated with the fixed ratio that they are coming from the minimization, problem. And we can do exactly the same thing, assuming that the musculoskeletal model will produce a negative torque at the crank. We can get very similar negative synergy. And just make sure that our synergies make sense. We compare those with some of the data coming from the literature. So the black line here shows our optimal positive synergy, and the red line and blue line are the EMGs or electromyography that captured from the skin of the muscle. And sees that they have a good agreement between these two. So we'll go forward and we'll use those in a feedback control system to be able to run our musculoskeletal model. So the figure on the top shows the framework. So we will measure the crank velocity and we'll compare it with the desired pedaling rate that we have. If our crank speed, the actual crank speed coming from the musculoskeletal model, is less than the desired value, the PID controller, the PID block, will suggest that we have to produce positive torque at the crank. And since we have to produce a positive torque at the crank, it means that we should activate the positive synergy. So we'll go to the positive synergy map, and based on the crank angle, we activated muscle accordingly to produce that positive torque, which results in the increase of the crank speed. And similarly, if the angular, the velocity of the crank, the actual value, is more than the desired value, the PID suggests the negative torque at the crank, and then we will use a negative synergy to reduce the speed. So we did a very simple example to maintain the pedaling rate of 106, the figure on the right, using the same PID controller, just assuming that there is no resistance at the crank. So we can see that the PID controller, a simple PID controller, is able to maintain the speed. And the figure on the bottom left shows that the muscle activation comes from the synergy. So the blue line represents the positive synergy, and the red line represents the negative synergy. It shows that to be able to maintain that, we need to activate both positive synergy and negative synergy. Just have in mind that this is the special case of the no resistance at the crank. But we know that in reality, there are resistance at the crank. And we did a very simple quasi-static power balance of the bicycle model to be able to calculate that resistance. So we assumed that we calculate the power loss because of the change in the potential energy, just assuming that the bicycle going up the hill. So we calculate that. We calculate the power loss due to the rolling resistance and due to the drag force, and also due to some frictions that friction losses in the wheel bearings. So if we combine all of those, this is a total power loss, and if we equate it to the power generated with the by the neuromusculoskeletal model, if we equate those, it just means that we can maintain our speed. So based on that equation and equation at the bottom, we are able to calculate the required cyclist torque at the crank or the resistive torque at the crank to maintain the speed. So if we perform this simulation in a whole framework, including the cycling resistance calculated from the previous slide, and we perform the pedaling rate of 106, trying to maintain on a speed, and we're assuming that we have a slope grade of 10%. The figure on the left shows the different combination of the resistive torques from the gravity, rolling resistance, drag, and the total, which is about 100 Newton meter. And then the figure on the right shows that the simple PID controller again is able to maintain on a speed. So obviously, if we use a more advanced controller, then we will have a better tracking characteristic. But we're just only showing that the PID controller, simple PID controller, is able to track the desired speed. And in the figure on the left here shows that since there are a lot of resistive torque at the crank, so now the positive synergy is only active. So we always have to produce torque to overcome the resistance. And the beauty of this approach is now we were just talking about synergies, controlling synergies, but now we can look at individual muscles and see how those muscles are activated. So the blue lines here shows the VASI muscle activation of the left leg, and the red line shows the VASI muscle activation on the right leg, on the right figure. And but to just improve the fidelity of the model, we also considered a neuromuscular representation of fatigue in our individual models. We added a fitness value to each muscle, which fitness of 1 or 100% representing the muscle is fit, and the fitness of 0 representing the muscle is totally fatigued. And based on this first order differential equation. But basically what this equation says that if we activate muscle with 100% as shown in the figure, the muscle force producing capability is reducing. And if we deactivate the muscle, the fitness value or the force producing capability is recovering. So if we include that in our model, in the individual muscles, and perform the exact same simulation, but here for the longer time, previously it was 2 seconds, just 2 revolutions. And now, if we do that for 2 minutes, we see the figure on the left shows the fitness value associated with individual muscles. And you see they are starting from 100%, but after 2 minutes, some of them are below the 50%. And what happens that at that point, we are not able to produce the required resistive torque at the crank. And therefore, we cannot maintain the speed. And for example, in the figure on the right shows that at the 100 seconds, we're not able to maintain the speed. Therefore, the crank angle is less than its desired value. And if now we look at the individual muscle to see what exactly happening, so the blue lines here shows, the red line shows the actual muscle activation level. So because there is some fatigue in the muscles, so the actual activation level is reducing. To be able to keep that constant, we have to increase the comment. So we increase the comment, which physically means that we are recruiting more motor units in muscles to produce force. So we increase the recruitment until it gets to until when we don't have any other motor units to recruit, which is within here, it means 100%. When we get to the 100%, the actual muscle activation or the actual muscle force producing capability of the muscle reduces, and it gets to some points that we cannot produce the desired torque at the crank, and therefore we cannot maintain the speed. So this is my last slide. I'm just gonna conclude with that we were able to develop a musculoskeletal model, which is verified through the kinematics data and EMGs or electromyography data. And we were able to develop a closed loop control of a musculoskeletal cycling model. It's closed loop, and it's very, and it depends on the situation. It can be real time, therefore it can be used in rehabilitation sciences for therapy. And we also were able to include the effect of the muscle fatigue in our individual muscles, and we were able to study that, what happens for the long simulations of the cycling. For example, if we want to simulate endurance cycling. And as a future work, we still need to validate our muscle fatigue model, and it can be used as I had in my first slide for the motivation slide. We're able to optimize the pace strategy. We're able to optimize the best seat position to produce the maximum biomechanical power. And as to improve our fidelity, we should also add the ankle joint to the model. For the last slide, I just want to thank Canada Research Chair and NSERC programs for supporting this work, and also Canadian Sport Institute for their collaboration in this work. Thank you.
Many thanks for a great presentation, Dr. Mehrabi. To wrap up, let me introduce you to some of the products that were used in this project. MapleSim is our tool for multi-domain system-level simulation. It allows you to quickly build models of complex dynamic systems by selecting and connecting components from a large library of pre-built components, covering a variety of domains like mechanical, multi-body, control, thermal, electromagnetics, and hydraulics. We also offer specialized libraries for batteries, drivelines and transmissions, tires, advanced hydraulics, and pneumatics. It's important to note that unlike traditional tools like Simulink, connections between components represent physical connections and not just signals flowing in one direction. This greatly simplifies the modeling task and dramatically reduces the complexity of the resulting block diagram. Maple is our interactive environment for mathematical analysis and design exploration. A full programming language allows you to script and automate analysis tasks, but also allows you to define custom modeling components from first principles for MapleSim. The Maple document interface allows you to easily capture every step you take, and the resulting interactive documents are easy to share, review, validate, and reuse through your product design or PLM systems. In all, Maple provides you with a rich and powerful environment for design and exploration and capturing the knowledge behind it. System-level models are an essential ingredient in verifying and validating a design. Simulation models can be deployed to a real-time environment, connected with controller and sensor hardware, and used for HIL testing, operator training, and system tuning. Unique to MapleSim is our ability to generate extremely fast simulation code, which gives you a lot more flexibility to use more detailed models and still meet real-time constraints. Code can be generated for many different target environments, including Simulink and LabVIEW. Finally, the Functional Mockup Interface, or FMI industry standard, opens up additional opportunities for integration with a growing range of supported tools within your own toolchain. Maple and MapleSim are very powerful tools and enable a model-driven innovation process in your own engineering research work. In addition, Maplesoft has a lot of expertise in system-level modeling, design validation, and HIL testing. We have worked with dozens of engineering research organizations around the world to help them take advantage of state-of-the-art techniques and tools to allow them to deal with growing complexity and to succeed in their own research goals. Our mission is to help make your engineering projects succeed, essentially to achieve more in less time, reduce project risk, and produce and share better results. With that, many thanks for your time and attention today. If you'd like to find out more about this project or how we can support your own research project, please send an email to webinars@maplesoft.com. Once again, thank you all and goodbye.